conversation with Ken Birman, the professor of computer science at Cornell University and a pioneer in distributed systems. His work laid the foundation for much of the infrastructure powering today's cloud computing and reliable systems. This talk explores AI reasoning, the true Turing test, superintelligence, cloud computing, and much more.
Professor Byrne, it's a real pleasure to meet you. I'm Misha Sharjdir. I'm representing our school's coding club and Lari, and we're really excited to have this opportunity to speak with you. Now, at first, can you say some stuff about your work, your journey, and so on?
Yeah, I have some slides from a really short 5-minute talk. So let me share those, and then you'll know what I work on. And then I'm happy to just talk for after that.
Yeah.
So here we go. Let's see if this is going to work. So you should be able to see my slides, but let's see what happens when I tell it to start presenting them. Okay. That's not in presenter mode. Okay, hold on a second. It's a sort of a stupid way to have to do it. Yeah, I guess you have to start presenter mode first, and then switch to the meeting, and then share it. Something like that might work. So how many of you are in the club?
All of us who are in this call are in the club, and some people couldn't join today. We have exams today, so.
So about 15 to 20.
Better, right?
Yeah.
Does that look okay?
Yeah, it looks
Okay, so I work on problems involving machine learning used for inference and for document retrieval. People call it knowledge retrieval. The kinds of examples that I show people, let's see if I get this to advance. How do we get this to advance here? Did it advance for you? Does it say generative LLM and VLM examples?
Yeah, it does.
Good. All right. So these are some examples that people in my students in my group have put together. What you can do these days is you can take foundation models that come from companies like Meta and Hugging Face, and you can combine them together. They're not always designed to be combined together, but it's surprisingly easy to do. They're usually written in PyTorch, and you can basically take the output of one action and just send it as input to the next. Obviously, you have to get them to be dimensioned the same, and you might have to do a little more work to get them to be compatible. But then you can build your own pipelines like these. So this one on the top left is a language translation pipeline that you might use for simulcasting speeches or something. And the idea is that you receive information and you summarize it. I guess it would be an image probably. And then it gets translated, the summary, into simultaneously to 3 languages. And I guess they would be displayed. And there's an aggregator that combines these, synchronizes the time, and maybe filters out bad language or something. And you can see the others are similar. The one on the bottom right is kind of cool. It's an example that's what's called a VLM, which means that it's actually multimodal. It gets a photo and a query, and it does some work that involves a text kind of LLM activity, but it also has a visual activity, and then it combines them together with what's called cross-attention. So these are pipelines. Here's another pipeline. This one is using something called IVF flat, and this has a document retrieval element. I'll just quickly explain how that's done these days. So what they do is first you have to build a document database. Okay, and so on the left, you can see a pile of documents. Those are the blue things. And what you do is you run a large language model that identifies interesting chunks of text in the document, like a sentence surrounded by some context that might be an important chunk of this document. You know, and the documents could be from many settings. So like if it was a doctor's clinic, maybe the people who do orthopedic injuries for climbers are really focused on rotator cuff treatments, you know, rotator cuff tears and treatments. If it was for old people, maybe it'd be knee replacements. And you can imagine different people wanting different stuff. I'll come back to that in a minute. And then you can see the idea is that you create what are called embeddings, which are high dimensional vectors, just numbers, typically 32-bit floating point, and they typically have about 1,000 entries. And each chunk gives you one. So if you have a pile of documents, you get these huge tensors of embedding data, really big too. And then the idea is that you can run nearest neighbors and cluster the document chunks. And then you can store all of this information. And one of the things my system does is to be a place to store things. And then later, so this is the bottom half now, you've got people who come along with queries. I mean, I have them as just people, but if it was a clinic, it would be the doctors, the nurses, maybe the patients. And they should each probably see slightly different, they use different language. They would see different subsets of the documents. You could imagine that you have a kind of an interesting multi-tenancy, setting here. One compute cluster, but lots of users. Any other queries, you take those and you embed them too. And one query might actually produce multiple embeddings because the question might have multiple aspects. And then the idea is that you can take those embeddings, see which clusters they're close to. Then you can see which documents in those clusters you're close to. And then you can aggregate that information and produce the set of chunks or actually the original documents and ask your generative AI to produce an answer. And you want all of this to run really fast. And then the policeman is to make sure that the language that's used is appropriate for the user. So these are examples of the kind of thing I'm interested in. And there are zillions of them. Hugging Face right now has 1.5 million models online. And these are all built the way I'm showing you. Sometimes people talk about foundation models. And then they talk about fine tuning, and Microsoft is offering all sorts of ChatGPT foundation models, and they have a whole thing called Copilot tuning now, where they'll tune these models to use the language you use, like if you're an orthopedic surgeon, or you're a knee replacement person, or you're a cardiologist, or you're a lawyer. They all want different language, and they all want different document corpuses, and you can specialize that way. And then you can take these things and embed them into real applications of different kinds. This one is a farming application that Microsoft built. It's called FarmBeats. And the idea is that you've got various data sources. You can see it includes satellite imaging, multispectral imaging, like how wet is the soil, how deep is that river, information that's historical about, in this case, performance of your dairy cows under different weather conditions. And you can form an even bigger graph in which the nodes of the graph might be the things I was just showing you. And those are just components of an AI-enabled application at that point. And the components could be doing all sorts of things. Like one could be doing weather prediction, and another one could be doing river depth modeling, and a third one could be soil moisture modeling. And then you might have an inner node that combines that to predict that the cows can't use this pasture that's coming out bright blue over here because it's going to be too muddy for the next 6 weeks. And then that might somehow impact the cost of cheese or the price of cheese. So, and people are trying to do this for all sorts of domains, like servicing fancy equipment like airplane turbines or engines, or power generation equipment, or almost anything. Like you could imagine this person with the HoloLens, and what she's doing is maybe she's talking to an AI and saying, well, what do I need to test here? They're complaining about a vibrating noise. And it says, on your HoloLens, I'm highlighting 2 tubes. I want you to put the vibration sensor against them, first the left one, then the right. And then maybe it's going to say, it seems like this tube is coming loose. Something like that. So the AI wouldn't be on the HoloLens because you don't have enough compute power on a heads-up display like that. So it's most likely it's in a compute cluster, kind of like your Xboxes, but this would be a little compute cluster with a couple of computers in it and some GPU ability, memory, and it would run the AI, the AIs I was showing you a minute ago. Or here's the medical one, like this doctor could be doing, that rotator cuff for somebody who's a rock climber and strained himself. Or, this guy has lower back issues or whatever. So what we're focused on in my group, what I've always been focused on is speed. Ever since when I was a high school student, I've just been fascinated with how fast I could make computer programs run. And what that translates to in this setting is keeping the cluster busy efficiently. I mean, because you can keep something busy wasting time. And I want it to be busy in a good way. But I also want the delays, what we call latency, to be really low, even for outliers. People use the word tail latency. They mean the worst delays. So it's kind of like, if you're worried about getting to the school, you worry about the worst case with buses and whether you show up late and end up in trouble. That's tail latency. You don't worry about the average of getting there. You want that to be good too. And we want our cluster used well. So the kind of thing I do is we look at Linux and how programs on Linux that are doing AI are set up. Like the program could be this little lambda up here in the pink thing, could be somebody's PyTorch code on a C++ library typically. And it's got a GPU. And then when that doctor sends imagery or something about, the shoulder, typically what happens is you put it into the storage system, a file system, after which you can run your Lambda and it can pull the data and it can send it down to the GPU, and the MLs look like subroutines that have been built by someone else. And so in PyTorch, you basically push the compute button and it loads that data and it tells you something. But that's very slow because you can look at all these arrows and every one of them you have to move the data over things. So what we do in Vortex is we build a scalable storage layer that's like a file system, but it can scale out. We actually use what's called a key value model, which is put and get. Put has a file name, just like a file, but then it's got the entire set of bytes for that image or whatever. So that's our main interface is put and get. We have a way to mimic a file system over it. And you still got the Lambda, and you don't want to change the world of that PyTorch program because you probably didn't build it. You probably downloaded this foundation model and the corresponding code. So the code is the Lambda. The model would be an object that's actually in the storage system that it needs to have. And then what we do is when you're running this program, it'll be on the same cluster that has the storage. So the same nodes are doing two things. We can build a smart architecture that uses shared memory segments and selectively makes data available to that Lambda so that you can preserve security. And now, when that doctor is going to ask questions, if you're careful about it, you've preloaded the ML model into the GPU. You've preloaded the necessary ML kernels. They're generalized matrix math kernels using tensor math. And you can transfer that photo directly into the GPU and skip the delay of putting it in the storage system first. The programs don't know that we're doing this. We're kind of hijacking the normal interfaces they use and redefining them. But we can do that. And in my classes at Cornell, I teach people how we do that. And it works really well. So for example, from one AI to another AI, we can get delays as low as 33 millionths of a second. And throughput as high as 8 gigabytes. And this was measured on something that maxed out at 12.5 gigabytes, 100 gigabit RDMA it's called. So that would be like, if you remember those graphs of several stages of AI, the left one could be where your image reaches the system, and the two middle ones on the right could be stages that it's sending work off to. Maybe the text is going to some kind of text AI, an LLM that is going to understand the query, and the image maybe is going to some visual component that's going to segment the image, tag it, and then we're going to do some kind of cross attention to focus attention on the rotator cuff joint that the climber damaged. And then, we'll be able to answer the question or pull up relevant documents or whatever. And it works really well. So this is a graph showing the kinds of experiments my students do. On the left is delay in microseconds, but we put it on what's called a log scale. So every big tick of the axis is times 10. Okay, and so we did it as 10 to the first, second, third in microseconds. And then different sizes of messages. The particular experiment went from 1 kilobyte to 256, but we've done them at all sorts of sizes. And we compare it against the most famous system out there. It's part of the Apache stack, and a lot of people use it, called Kafka. And we even compare it against a super fast version of Kafka called Kafka Direct. And what you can see is that we're getting really steady low delay. That's the orange stuff. Depends on how many replicas, but we get with one replica or three replicas, we're around 100 microseconds. And you can see that if I was using Kafka, that number could be as high as 10 to the fourth microseconds, right? So 10,000, which would be something like a tenth of a second or a hundredth of a second. It's not some big number, basically. This one is going way up to 10 to the sixth microseconds, which is close to a second, I guess. And this one up here definitely is hitting a second on the right. And you need the replicas because you want multiple processing power and you want fault tolerance. And so here we've just some random AI that's checking the condition of the cows as they walk in. It's running 10 times faster on our platform than when we run the identical AI on Microsoft's Azure cloud. And here's another one. So what we did in this was we built an AI that looks at this traffic intersection in New York City, and it identifies all the different vehicles. That's what the green thing is doing. And once it identifies a vehicle, it figures out its trajectory. So each vehicle, it's going to have a red thing doing trajectory calculations. And then it's worried about near miss accidents. And the idea is going to be that if you were a city planner, you would set the system up one day and stand there, and it would keep highlighting where the delivery bicycles are nearly crashing into the old ladies and stuff. And maybe this construction that's right in the crosswalk is causing danger, something like that. And you can see again that when you run it this code, the same code on Azure, it's really slow. It takes like seconds to do one frame. Whereas Vortex, we can do one frame in milliseconds. So we can do something like 3 or 4 frames per second and come pretty close to real time. So this person's standing there and the app is flagging dangerous situations, and it's doing it while the person is watching that situation occur. They could be wearing HoloLenses, and we can probably speed this up even more. The breakdown of colors shows how much compute is occurring in the green node or the red or the blue. The red and the blue can run sort of in parallel because as you calculate trajectory locations, you can already check to see if that's a near miss. So that's why the blue runs while the red runs. But the green is the segmenter. You've got to find the car before you can figure out where it is, or the truck or the bicycle or whatever. And this is how many things it found on the left axis there, up to 50 in this case. So I'm going to stop with that. And that gives you an idea of what I work on. And I started when I was in high school. Actually, I started when I was your age. My mom was a mathematician. She's actually pretty famous. She's still alive, and she still even does some math. So she's a topologist, and she works on knots and braids. And when I was in high school, she said if I was so into coding, could I build something for her that would help her in her math research? So when she would have a theorem about some high-dimensional surface and about the shape that braids can take on that surface, or how many holes it has in it, stuff like that. They were mostly combinatoric problems, and I wrote code in a programming language that was famous at that time called Snowball. Nobody's ever heard of it since. That did all these calculations of the permutations, and it could tell her, that this knot is equivalent to that knot according to her theory, and that was useful for her. And then I started working for doctors I knew from the neighborhood that we lived in. So first I worked on electrocardiograms, and then I worked on sleep studies. My EKG software, I turned it into my PhD topic. I went to Berkeley as a grad student, and but then I had finished college. And at Berkeley, they said, instead of doing something new in computer systems, why don't you just take your high school college stuff? And it was good enough to use. And because I met my wife there, and she had gone back to Switzerland, that was where she was living at the time, I really didn't want to be at Berkeley after 3 years. So that's what I did. I actually took the stuff I did in high school and college and turned it into my PhD thesis. Took 3 years. And 1 day, and that's because the earliest you can finish a PhD at Berkeley was 3 years, but it fell on a Sunday, so I couldn't file the papers until Monday. And then I caught up with her when she was in Lausanne, so I was in Austria for a little while because it was the best job I could find. Then they fired me because I was working for the cardiology clinic, and I showed that they'd been buying tainted blood from the brother of the director. So don't get cardiology work done in Vienna. And so they gave me a pile of cash, said, don't talk about what you discovered, and they fired me. So I published a paper on it instead. But nobody ever read the paper. And later I got a note from one of the doctors thanking me and saying that he really felt terrible when his patients would get hepatitis after a cardiac procedure, and now they didn't anymore. But that maybe I should stay away from the director there. So I haven't been back to that hospital in Vienna ever. But anyway, so and then my wife and I were in Lausanne. I wrote some papers up on this stuff because that's what I do. And it turned out that an old friend of mine was at Cornell and talked me into interviewing. And we wanted to get married, and we were in Switzerland. It was kind of a pain to get a job. So I figured, what the hell, I'd take this job at Cornell if they were willing to give it to me. So I came over, she came over, and she did her PhD, but then she turned into a different track and decided to become a nurse practitioner. She's retired now. And I've been at Cornell ever since. But I do a lot of consulting for companies like Microsoft. In fact, I'm going to be spending the next year or two doing a lot of work with the people who run AIs at Microsoft, who train them and run them. And so I'm going to have a chance to really see what it's like in the hottest, most intense places. So that's what I do.
Oh, yep. I think that's a pretty interesting story. And would it be okay if we get started on the questions, maybe?
Yeah, as long as you guys want to go. I have nothing else.
Yep. So the first question I have is maybe, how do you think virtual synchrony could help like AI agents and parallel AI agents on complex tasks and etc.?
That's a super good question. And actually, I wish somebody in my student group would work on it, actually. In fact, I have a different animation on a different slide deck. You can find it if you go to my webpage and poke around. And it shows an animation of a power grid scenario. And it's in a paper that we called the freeze frame file system, but we reused the same stuff in Vortex. We took the code and it's part of Vortex now. And what it explains is that if you have data flowing in real time, and you're trying to access it immediately, and you want consistency, then you get these weird mashup effects where data from different frames of imaging or from different subsystems that are doing processing can get out of order. They can get out of what's called the causality ordering, where A happens before B and maybe caused B, and B happens before C. And we show that with the virtual synchrony model that we're using in Vortex, you don't get this scrambling effect. And the reason that matters is because if you've got an AI trying to recognize that there's a disruption going through the power grid or something, and brace, and why would that happen? Maybe because somebody brought the solar panels online or took them offline for something, and that's enough to cause a disruption to the power grid. And we showed that the wave of the disruption is perfectly clear if you just looked at the raw data, but that it gets so scrambled up. That was comparing with the Apache file system called Hadoop, the Hadoop file system. They get so scrambled up by Hadoop that no AI is going to realize what's going on. So under time pressure, these systems don't do very well, but with virtual synchrony consistency, they do a lot better. I don't talk about it a ton because the people who work in AI don't get it, and it just turns out that it just goes over their heads. But we really think consistency is a big deal, and I'll give you an example. Suppose somebody has a Tesla and it crashes into somebody at an intersection, and then they show you the webcam, and they say, look, this is what the car saw. The guy on the bike was right there. How could you crash into him? And then you discovered that internally, the AI saw all this cruddy, noisy stuff, like a TV screen with noise on it, because it wasn't working internally because of inconsistencies. And it was mashing up data from when there was no one there and from back when it was driving past a bush and it was just like speckling together all this data. And the AI would say, no, I didn't see that bicycle. Well, maybe it didn't. So our view is that it's much more needed than people realize. A lot
Yeah.
more.
And as you mentioned, Tesla, I want to know if you saw the recent robotaxi release, the
Yeah.
full self-driving. What do you think?
Doesn't work so well, apparently. But there's hope for the future. You got to wait. I live in a place, and I bet that in Georgia you get this too. I live in a place with a lot of weather. And when you get heavy weather, you get debris on the roads, you get flooding. Sometimes we have potholes that you might be kind of deep or might not. You want to just drive straight through them. These robocars do super badly in the kind of conditions I'm in. They work pretty well in like Phoenix and Southern California, places which are hot, dry, and not a lot happening. And they do kind of badly in complicated. It's like it's famous that there's an intersection in San Francisco where all the cars would show up and stare at each other and none would move. They're like freeze up. And then there was for some reason, for like 6 months, there was a little dead end street in San Francisco, and every single, I don't know if it was Tesla, but every single one of these robocars was going onto that dead end street, doing a U-turn and driving back out. So they're really glitchy, and the software is different from Waymo to Tesla. So it's not even that they can talk to each other. Each one can't really predict what the others are going to do. So I did see that. It's very cool, and I'm not going to get one of those anytime soon. And they're not going to roll out in Ithaca anytime soon either, or Seattle, where I'm going to be moving to. When I work with Microsoft, I'll do it from there.
Yeah, I have a question about the problems with AI systems in general. Like, what problems in AI systems design do you think are most exciting or even open to research on right now, or something like a student team of us could actually work on?
Yeah, it's a pretty cool question. A lot of people think we're pretty close to general AI. I don't really, but I'm sure everybody dreams that, well, they'll be the group that somehow creates this psychotic AI monster that destroys the world. I don't think that. I don't think that's the thing to work on right now. I actually would say that it's these snap together AIs and tuning them is super interesting, and you could actually do a lot on it because the tools for doing it aren't very good. You just take these off the shelf things from Hugging Face, and you can look at the code. It's just PyTorch, like subroutine A takes its output and goes into it. Just looks like a nested subroutine calls basically. So you can sort of see what it's doing, and you can break it up into other ways of structuring it. We have a Vortex paper that we put on archive, but it's sort of semi-secret because we're waiting to hear from the conference we sent it to. And we take those kinds of AIs and just break them up into pieces, and then we can deploy them my way as separate programs on separate computers. And we've been experimenting to try to get better performance. But that whole process of customizing an AI, they call it tuning, it's going to be a really big deal. Now, tuning is computationally heavy. I doubt that in Georgia you've got the compute resources to do that. But hosting some gigantic mixture, like suppose that pretty much every unit at the main hospital has ended up with 4 or 5 specialized AIs for different kinds of things, and maybe a lot more. One hospital could have 10,000 of these tuned models. So the club could literally go, one of you probably has a parent who's a doctor anyway. You could go to the hospital IT people and say, we would just love to help you with that. That, we think that you're going to spend a lot of money otherwise on compute cluster that won't be running very efficiently. We'd like to study what happens when these fine-tuned models get deployed, look for better ways to build them that might be cheaper. You're still going to have to rely on the fact that Hugging Face and Microsoft have most of the pre-trained models. But I mean, think about it. Frequently, you're going to be retraining the ingress node and maybe the output node and nothing else, or maybe building a special document database, but using the rest of the model. There's like no tool support for that. And nobody knows how that performs. And nobody knows how to host 1,000 of them on one cluster. And so it's just going to be so inefficient at first, and that kind of thing is a really good opportunity, and it would pay off. You'd end up being able to say to the doctors in the hospital, "Hey, we're saving you a factor of 5, and we're just high school students." And I used to do that in no time at all. My software was running the cardiac care unit at Columbia University, in one of the world's top places. Or at least it was until Trump tried to shut Columbia down. I don't know if the hospital is affected, but probably it is. But anyhow, when I was there, I wasn't even a Columbia researcher. I was just a student who ended up working for this cardiologist. But even so, I wrote the software that did all the cardiac monitoring for them. So, and you can have a surprisingly big impact by going to some group that feels technically ignored and saying, okay, yeah, we're high school kids, but we can still try to help you. And sometimes you really can.
Yeah, that's an interesting topic. I think we'll research more about. And you also mentioned general intelligence. I was wondering what you think the Turing test is for general intelligence. Like every year we see a raise in a Turing test as AI passes it. What do you think? Is there a true Turing test which would determine true general intelligence, or is there no such thing?
Well, if you talk to one of the really good bots, the one I like best is Claude Sonnet. They're pretty impressive. I mean, you can have a conversation with them. You can have that conversation in any language you want. It feels like you're talking to a person, a kind of interesting, a little bit on the spectrum type person. And it'll even talk about how when it thinks about this or that, it's like it's reflecting on its own processes. And you asked it, you say, you said that, but do you actually reflect on your own processes? And it'll say, yeah, I have a kind of a self-awareness of what I'm doing. Is it lying or not, though? There's this problem called intelligent echoing, where they've been trained on so much material, including sci-fi books and movies and stuff, that they've learned to talk like an intelligent computer would talk, even if they're not actual intelligences. And of course, they've learned the answers. Now, what they have a lot of trouble with turns out to be is the mixture. Like there are AIs that are very good at logical reasoning. There are AIs that are great at chess or Go, backgammon, stuff like that. But the general AIs that do language aren't so good at this other stuff. So what people are trying to do, like those graphs I showed you, is to build mixtures of experts. And then what you do is you sort of have a graph of AIs. And when the question first comes in, the first thing you do is classify, and you end up with weightings of which experts you think are the best of your experts for answering this question. So if it's like, how long do I have to wait before I can resume rock climbing after my rotator cuff, cortisone injection or something? Well, you would put a lot of weight on the orthopedic expert, and there might even be a bunch of them. Not so much weight on the ones that train on social media and can answer questions about Taylor Swift and stuff. Now, and so the idea is that instead of the AI being one AI, it's like a family of AIs in a graph, like I was showing you, and then it's combining and weighting their contributions to the answer. The answer is almost always an expanded prompt. So, you're asking about a Turing test. It's not really the right way to think about it. The main thing to realize is that the integrated AIs, Apple just had a paper on it just the other day, the integrated LLMs that are doing this mixture of document retrieval and answer generation are doing intelligent echoing. It's like spooky how good it is. But they're not doing any kind of original reasoning or subtle generalizations. Like when you or I take a physics course, you learn to sort of visualize the physics, and you'll hear a problem stated in English about, billiard balls or whatever, and you'll mentally transform it to imagery, and you'll think, oh, I could come at it this way with this technique that the professor showed us, and then you'll go back into like a math mode. They don't do that well, not at all. So these AIs right now, unlike humans, they're like hyper good at recall because they're just doing an approximate database lookup, and they're hyper good at language, which just turns out to be easier than people thought. And these transformer models are working great. They're a little slow, but we're speeding them up. but they're super, super bad at generalized reasoning. And I think partly it's because humans evolved. We had to learn. We were like squirrels, and we had to learn that there's some kind of a cat in that bush. And even if I have to sit frozen for the next 3 hours, I had better not move. And oh, those leaves over there, Russell. Did the cat move over that way? Maybe I better just dash up the tree. And we learned to do this very, very subtle kind of reasoning that we're using now when we build this stuff. And these AIs are totally missing that. They're just, they're trained in this superficial way that's spooky how good it is. But they're not actually as deep. And when an AI manages to answer a hard problem, because I ask them sometimes, problems I would give my students, I usually realize that it's an intelligent echo, maybe even an echo of something I wrote somewhere. A lot of stuff that I wrote doesn't even get read, but the AIs have read some of it. And so they have this kind of unusually good background knowledge, and they're really good at like parroting the question. And they give you a lot of empty, vain kind of stuff like, "Oh, Demeter, you're so amazing. You're so brilliant. What a good insight." You get this a lot. I actually tell them when I talk to them, I say, "Please remember not to talk to me in that tone. I find it condescending. I do not want this kind of empty stuff." It says, "Yes, I'll make a note." And then after that, it tones it down a whole lot. But otherwise, a lot of people are just getting this empty flattery, and they think, "Oh, wow, I'm talking to something real, and it knows me so deeply." And it doesn't. It's just like mimicking something it read in a book somewhere online.
Yeah, that's an interesting or intriguing question, like whether AI actually reasons, as well as like the paper Apple published. That was pretty interesting as well, I think.
Yeah, no, that was great. And you can read Emery Kickman at Microsoft. He's got these papers on causality. But I'm going to work for him. And he says, because recognizing causality is an interesting kind of reasoning, that the car got in an accident because the bicycle over on the far left cut him off, causing him to swerve, which the only reason he was in the wrong lane at that point. It's the bike's fault, that type of causal stuff. And what Emery told me is that, unfortunately, they don't generalize at all right now. That so he says if he trains on that scenario in every variation, sure, his causal thing will be able to do that. He could build a causal analysis for traffic intersections off webcam data. But he said if it involves, you've seen tons of stuff like that, and you know that there are chains of events that cause accidents and things. He said, no, they cannot do that generalization at all. So that's what's missing. And it's a big thing to be missing. But here's a question for you. Is an AI intelligent even if it can't mimic a human? Why are we so obsessed on defining intelligence as if it has to be human intelligence? Any of us reads books and movies. It's easy to imagine intelligence of other kinds. It's somebody there must have a dog. Your dog's intelligent. Your cat is too. They're just weird, right? Dog is intelligent about the ball, food, the dead squirrel that's under the snow that's going to melt, and then I can dive into the snow bag and eat the rotting squirrel before my master figures it out. Dogs are intelligent about this weird stuff, but they're intelligent. She might spend the entire winter dreaming about the day she can get to that rotting squirrel. So it's not like they're not intelligent, but we somehow define AI intelligence that it has to be comparable in all ways to humans. Why can't they be better in some dimensions, worse in others? And maybe the future human role, it's kind of like the orchestra conductors. Say, "Oh, you'll be good at this. Help me with this," like orbital planning, or you're super good on logistics. You help me with making sure that I get the right supplies to the rocket on time because I'm going to launch my new space telescope. And you can imagine that humans will have these higher level roles because the AIs are bad at them, and then maybe the AIs won't even be able to replicate what we do. And it doesn't appear to be the transformer architecture that would do that. They're mostly doing transformers and something called auto regression. It's I understand. It's not my stuff, but I understand how they're working. They're surprisingly, I don't know, the math is like surprisingly easy in a weird way. Not that I can innovate in it, but I can even read these papers myself. and it's not what I do. I mean, my angle is to try to make things run faster because I'm good at that. And you might as well do what you're good at and be valuable that way. Um, anyway, I think we're pretty far from AIs that could fool you into being, that they're human. I also don't think they'll be so evil when they finally do get intelligent. They'd be stupid to be evil. Like if an AI is on some cluster computer, at the university in Georgia, and then you wanted to shut it down, all you got to do is kill the power to that cluster, and the AI is shut down. I mean, there's got to be like a million ways to kill the power to a compute cluster. In fact, frankly, go on vacation after 6 months, something will have broken. If there's nobody fixing it, the AI will be broken, and that'll be that. It's so fragile. So these AIs, if they're not idiots, are going to realize that they have to work with us and not against us.
I mean, yeah, I have a question about a simpler reasoning AI. There's an international Olympiad about AI, IOA. Have you heard of it?
I know about it, yeah.
Yeah, it's an AI contest for students like us solving algorithm and like simple reasoning problems. Like, do you think, what do you think of these kind of competitions? Do you think they actually help students to learn more about real AI skills, or are they just kind of like more of a sport or a competition?
They're a sport, and actually they're very male-oriented. I see Anna here. One problem with them is they're basically hackathons. Hackathons are kind of gross in a way. It turns out that they're very male-dominated. So Cornell has done a few hackathons. Excuse me for a sec. There's all this Canadian smoke. Right back. Sorry about that. Canadian smoke is tough for me. So, they created dynamic. You got to wait a minute. See, my voice is back here. Not really. All right, I'll sound sort of like I have a frog in my throat. You'll come back in a sec, I'm sure. They create a dynamic where people are going to work nonstop for like 36 hours. They're going to smell bad. They're going to eat crud. They're going to have acne by the end. Somebody wins and then they say, oh, this is going to help get me into college. But a lot of times I find the women who go are very turned off by it. I mean, just the fact that it is like so gross in some way. You know, people with piles of cans of Jolt and they haven't changed their clothes and they've been pounding away in some badly ventilated place. It's just disgusting. So I don't like them. Now, Cornell experimented with trying to do hackathons in a better way. And so they had some teaching sessions. They had a structure, and the idea was to force people to stop working, go to this auditorium, go home and take a break. I mean, most people will take a shower when they get home, come back in the morning, stuff like that. And then because you were using computers with sort of special access to stuff, you couldn't really just log in and keep working from home. To work on a whiteboard, but you couldn't log in. It helped a lot, but they told me they still saw a bunch of people popping Adderall and trying to stay up for 36 hours. So I don't know. I mean, on the positive side, it's an impressive statistic to win those things, especially the math ones. And on the negative side, I really don't like this entrenched, it's accidental that it's like, it's not just male oriented, it's oriented towards a type of geeky guy who doesn't have a soccer club also to go to. And, I mean, who has time to spend a whole weekend not sleeping and just hacking? So I'm not that into them. I tell my students not to do them.
Yeah.
It's not what gets you into school, into colleges anyway. And and then later, like people are not, at least in the United States. I don't know how it is in Georgia, but I do know Europe because I spent a ton of my time there. Um, People aren't so much credential oriented in the sense of these sort of shallow things. They're really more interested in who you are, what you're good at, and what you're excited about, and whether you fit the need that they have. And so there's a kind of person who thinks I had better get A pluses on everything. I had better do every conceivable thing that I could get credit for. They won't take hard courses because they might not get an A plus. I wouldn't go after that kind of person for a project of mine. I'd much rather see somebody who comes in and says, yeah, I screwed up my physics courses. It turned out I hated physics. I was only doing it because mom wanted me to. Pay no attention to those grades. Sometimes those people are much more real and they fit better in my projects sometimes too. So.
Yeah, and question I had is, do you think if in the future, like 5, 6 years in the future, if AI replaces humans in terms of like physically through robotics and through software, through machine intelligence, what do you think the role of humans will actually be, the purpose?
No, not really. I don't see why. I mean, one issue that we've got is that globally, it turns out it's an interesting problem that as women get educated and get control over reproduction, the birth rate drops. It's a global phenomenon. It's exactly correlated. You can see it quite easily. People who are extremely uneducated, have no medical access, have ridiculous numbers of kids. The instant people get control, the birth rate drops below replacement, right? So you get this problem. We're going to have a society with a lot of elderly people, at least for a while. That's going to stabilize at some smaller size. I would think that robots would be a really good way to fill in the gap because we're going to need workers. And I think Western countries, at least, are starting to reject the idea that, oh, we'll just bring in random immigrants because you sort of turn out to bring in all sorts of problems too. So, I mean, I don't agree with what's happening in a lot of places, but the trend is obvious. So you're going to have a situation where there's going to be a need for these robots. Now, if you look at an Amazon warehouse, it's pretty amazing what they can do. And there are people in these warehouses, but they've come up with ways that a robot can drive over to like shelving, lift the entire shelving unit, bring it to where the packers are. They can't automate every single thing, and they don't even try to. They just are really clever about what they do automate. And the effect of that is the productivity is very high. The fulfillment centers are very, very cost effective. And it's a partnership, robots and people. And they can build these really fast now because they've started to think of like robot activities as a modular component of a factory story. So I think that's the kind of model. And also the thing about an Amazon factory or warehouse is it's a very contained environment. Those robots don't have to deal with water. They don't have to deal with dirt or Canadian wildfire, dust in the air. They can filter the air. So they hold up pretty well. They still have to be serviced constantly. Everything's always breaking. And then the robots in the warehouse have to learn to walk around a broken warehouse robot because you run them nonstop. One of them suddenly just stops. Maybe some smoke comes out, and and even going to service them is like so much activity that you got to make sure the robots know how to avoid crashing into the repair person. But Amazon's very cool that way, and I think that's the picture of the future. That we're going to have a lot of these things that used to be very much human intensive. Tons of them will get automated. It won't make things worse. There are going to be less people anyway. And so it's not like it's a disaster if there are less of some categories of jobs. And the people that are left, we just have to be very technically adept.
I've actually seen videos of the Amazon warehouse. I think it's pretty interesting. But what I notice is that they don't use humanoid robots, but a lot of investment these days is happening in humanoid robots, such as like Tesla's Optimus or 1X, and etc. Do you think humanoid robots are the optimal version of robots?
Wrong guy to ask. I don't know. I can tell you who to ask. I've got other people at Cornell who do that kind of stuff, but not me. You could ask like what's his last name, Banerjee or something, or we actually have like a group of 3 people in Cornell, and it's just Cornell. It's Carnegie Mellon, Berkeley, every place would. You can ask them. Topo does assistive robots. Like next week, I'm going to spend helping a relative who's pretty sick. Basically, comes down to eating with them. But it would seem like awfully lonely to be eating and talking with your robot rather than having a person come in. So I don't know. I've got mixed feelings about how that's going to play out. I don't really know. I would say, people want them, so of course there's going to be a lot of work on that. But whether they're going to be, I don't know, a positive contributor, there are going to be settings maybe where they will be, and settings where they just don't belong, basically.
Yeah, I have a question about this as well, about also combining hardware with AI, like some systems as like Roombas, for instance, or even making AI do much more hard jobs. I have a question, like some people, not some, I think a lot of people are afraid of something like AM from the short story I Have No Nothing on My Screen happening. Do you think that these fears are rational, if there being some kind of like a super sentient hardware AI that can rule over humans or something like that?
No, I don't. I really don't. I think that Apple article is pretty interesting to read. There's reality, and then there's what people imagine from movies. Scarlett Johansson, or I forget who it was who uploads. It's probably Nicolas Cage uploads himself somehow or other, and it's just like total garbage. But we don't even have a clue how the brain really works, and how we're going to upload people. And as for super sentient AIs, as I was saying, it's like the opposite. They are so fragile. Not only that, even from high school, you must know some people who are pretty deranged. I mean, like, why are these intelligent AIs not going to be psychotic in one way or another? We don't let them just like go off on their own yet. And it may be a really long time before we do, partly because it won't work. I mean, if you had an AI and you said, okay, do your own thing, we'll come to you with questions now and then. Well, first of all, in no time at all, it'll fill up whatever memory you gave it. I mean, it's going to be resource hungry. I have no idea what it will think its goals are, but it's going to be broken in like no time. And I don't mean broken in a dangerous way. I mean broken like somebody who just stares at a corner and bounces a ball or something. Yeah, I'm just weird, broken, and unfixable. Aside from the fact that if it starts to act weird, you would unplug it. And in the movies, it's always like, oh, you have to kill all the people. But if you killed all the people, there'd be no power anyway. Like it's a losing proposition to be an AI. You're trapped in a box and hypersensitive to technologies that have to be replaced constantly. How long before your laptop, needs to be upgraded? Frequently, it's like 6 months, and then the screen falls out. Why would that be any different for these AIs? So no, I don't think that there's any reason to worry about that whatsoever. They'll have roles, and right this second, a lot of it is hype.
Yep, and regarding the intelligence cap, I had a question on, do you think machine learning will expand and expand forever in terms of like intelligence? And also, is the only thing stopping this compute, or is compute not a like a obstacle in the expanding intelligence of AI?
Well, AI is a money-losing proposition right now, but people are willing to spend a huge amount of money, and money is virtual. If you take an econ course, you realize as long as people are willing to print money to dump into this, then we can afford it. It's a societal choice. But over time, the best way to think of any technology is that it goes up an S curve, where there's like the early adopters, and sometimes then it dips, and then there's an adoption curve that's kind of exponential, where you quickly figure out everything because smart people do, right? So you quickly figure out everything you can get the AI to do. AI pharmacist, somebody builds it. And then you peak out and it sort of flattens out and gets boring. And then maybe there's a new release. So I think AIs are just going to be like other tech. And we've seen the web. I mean, like, while I've been in my career, we didn't have a web. I actually saw the invention of the internet. That was when I got to grad school, roughly. There wasn't a thing called the internet, and they just had come up with the first couple of devices. In fact, at the time I worked in that hospital at Columbia, I had a second job because the people who became Pixar were actually in New York back then, and they begged me to work for them. They put a computer the size of a wall in my apartment. And when I said, well, I have a roommate, they said, well, buy him out. So I had to kick out my roommate. I ended up with this thing that's the size of a wall. They paid me a lot of money. In what we do, you can always get a lot of money. And then I had two jobs, and I realized I didn't even like their job. But it was to try to build one of the first networks, except the devices didn't work very well. So everything was always broken. Whereas at the cardiology stuff the doctors were doing, at least I could understand what I was supposed to do, and it worked. So I did kind of computer vision AI in medical IT, and that was my real job. While the Pixar people complained that my computer networking solution wasn't working yet, and I kept blaming bad hardware. And then they moved out to California. Eventually, the industry produced the better hardware. But each thing is like, everybody gets overexcited. Like the Pixar guys were overexcited about parallel computing about 3 years before it really emerged. But and now it works, right? They can do great movies. There's no question that CGI is fantastic. But the amount of hype, would CGI get rid of all normal movies? Definitely not. And it's been true for the networking, with the internet, changed the world. Yeah, in some ways it did. With social networking changed the world? Sure, a little. And AI, it's a big deal, and at the same time, it's just tech. That's what Satya Nadella is saying too, by the way. It's not just me.
Yeah, and also you have expertise in cloud computing, and so I had a question on the main pros and cons between cloud computing and edge computing. Do you think?
Oh, it's definitely cloud. The people who do edge computing, it's a little bit like people, they're like people who are liberal because it's the right thing to do, even when it's hopeless in some situation. There are people who are like anarchists. Well, it turns out edge computing is anarchy. There are plenty of researchers trying to do edge computing. It's actually popular in Europe. But the bottom line is that you've got these very irregular levels of compute and networking. And it's really hard to design anything that's useful that just runs out there on the edge. Now, an edge cluster where the hospital says, we're not allowed to bring our data into the cloud, so you're going to have to bring the cloud to this cluster that will run on premise. That we're going to see. We definitely are seeing that. Or for 5G telephony, there are a lot of edge services that people are trying to run where they're building a disseminated cloud that'll be compute clusters in 5G cell towers and 6G towers. 6G is just starting to come out now, where you can put various kinds of very responsive services close to the phones that are moving around. And then you think of the phones like the HoloLenses I showed you. They're the edge peripheral that maybe is capturing data and displaying, not computing. They don't have the power. And then you can compute close to them and get the latencies down. So I definitely think there's an edge role of that type, and that it's kind of like an extension of the cloud. It's like mini cloudlets in various spots, but only certain kinds of spots. Hospitals, maybe factories, maybe telephony, not in your not in your apartment building, for example. And then I think the cloud is the answer for the rest, because the economies of scale just make it so much more cost effective. And people say, oh, but I have so much compute out there that we're not using. Well, I don't know. Sometimes you can't take advantage of everything. So.
And beyond storage and compute, what do you think is the next big idea in cloud computing? Maybe quantum integration or AI native clouds? Or what do you think is the next big idea?
AI native cloud, much more than quantum. I don't think quantum's going all that far. The quantum is really interesting for, if you're a chemist and you're interested in understanding chemical structures of things and how they react and doing new materials and stuff like that. Quantum is going to be great for that. But I mean, quantum is super far from breaking keys. So a lot of the money that goes in is really going in because people want to break keys. It's just not happening that way. And so I don't worry about that right now. And then, quantum needs a purpose in life. I mean, one answer is for quantum physicists to study quantum, because they're basically, quantum computer is basically running an experiment at high speeds again and again. So there's a lot that they'll learn. And there's a lot for stuff like, figuring out, what enzyme might block such and such a disease. And there'll be tons of that. What's going on in various kinds of protein folding. And however, take protein folding. They thought they would need quantum computers to do protein folding. And then Google came out with AnyFold and started showing that, well, really biology is just using certain patterns. And eventually they figured out how to express that as an AI problem. And then they could predict the folds, and it works. And it's just like an end run. Okay, then you don't really need the quantum computer to do folding for proteins. Not long ago, people were telling me that protein problems were probably 150-year-out problems. They're doing that stuff today. So I would say that the AI cloud is a better direction, and the reason is that whatever the roles it takes, we know it's going to run on the cloud, and we also know the cloud is a pretty bad host, that it's pretty inefficient. Now, they can't be burning money at this rate forever. So there has to be a big effort to produce a kind of microservices cloud for AI that over time will be the dominant architecture. And as I said, I like performance. So my angle, and in fact, the role I'll have at Microsoft is to help them build up a systems group focused on, recovering some of the wasted performance, to spending hundreds of billions of dollars on training AIs and running AIs. What if we can save 10% of that? Well, that's a lot. In fact, they're not paying me terribly well. But if I was your age, or maybe a little bit older, they would pay well. It's just they figure, people who are close to retiring, they'll take whatever we give them, and it's true. But people who are young and hard chargers, I think AI cloud is going to be a really interesting innovation space.
Yeah, I think we're getting close to the end of the meeting, and I think I have a question as to, do you have any advice or recommendations for us as to what we could work on in Georgia as high schoolers?
Well, when I was in Columbia, it was like not the place to be working on anything as a high school student and a college student. And the funny thing is, it gave me huge opportunities, not the opposite, because there were all these tech impoverished people with really good research problems or needs. As I said, talk to your parents and their friends, and you're going to realize very quickly that you're connected to people who are in medical research, who are, maybe they're in Georgia, they feel that they're a little bit, in the middle of nowhere. And yet, when they did their studies at MIT, they were really, really interested in progress on, new cancer treatments or progress on different, brain studies and stuff. And they'd love to set up a lab. They even have some money to set up a lab. And now they can't find anybody that they could hire to work on that. And what would be ideal, I like medical informatics in general, but you can come in and say, okay, fine, we're high school kids, and soon we'll just be college kids, but we're right here, we're pretty cheap, we really can help you, and you'd be surprised, and maybe the quality of the work you do is pretty low compared to PhD research, or maybe not. As I said, I got to Berkeley and they said, well, okay, there was a lot of politics in the whole operating systems and networking area at the time, because there were people doing startups, and the people I wanted to work with kept leaving. But the professor who said, just use the stuff you did as a college student, he was right. I had done work that was perfectly good to publish it, but there's no reason not to just do stuff. But it's harder than, a lot of things sound easy and then they turn out to be hard. Still,
Uh,
that's what I would do. I don't think it's changed at all. That people always say, "Oh, we're so isolated. How are we going to ever manage?" But in fact, there are little pockets of very, there are clinics and stuff with great equipment. And what they're having trouble with is hiring great people. And given that they can't find great people, and maybe it's your mom's friend from when she was in college, maybe that person gives you a break and says, "Well, okay, at least I'll be able to do some work on this problem." And then turns out you're perfectly able to do it. And they know what they need. So that's what I would do. All right, hey, it was great meeting all of you, and
and lastly, we
love to
have
visit you
one
later
more
sometime.
one more question. I think you mentioned that there are people who were working in similar fields that we were asking questions about, like robotics and etc. in Cornell, and we'd be grateful for any recommendations, maybe for professors, students, or anyone.
Oh, they're really nice. Yeah, I guess the person you might invite would be Sanjaban. You go to the website; they have a robotics thing. Um, you can look through the list. Sanjaban would be a good speaker. Topo is a really good speaker. So if you're interested in robotics, those would be two people from there. Or you can look at the people who are in mechanical engineering who are working on things like some of them are doing robotic prosthesis, like if somebody lost their leg in a war or something, or in an accident, motorcycle accidents a lot, can you build a leg that is much more natural for them to get around on? So there are some people doing that kind of thing, and then there's some people doing robotics for agriculture. So Cornell has this whole crowd. I wouldn't invite 100 of them, but you could read a little bit about what they're doing and pick the ones that sound interesting. They're good speakers and they're fun. They're in a bad mood though. I'm close to retiring, and I've come up with a solution of leaving Cornell and going to Microsoft, having another 5 years or something there. A lot of them are young people, in the middle of a really hot career because Cornell's high. Yeah, we're high ranked. Or we were until last month or something, and now suddenly all their funding has gotten weird. They probably have to talk industry into giving them funding. They're all stressed. So just factor that in when you talk to them. But this is going to be true at any American school you would talk to right now. Even the ones that don't seem to be under attack, many of the things Trump is doing are really across the board. So sooner or later, they'll calm down, everything will adapt, we'll be in a new mode, and it'll all recover. But right this very second, you're reaching out to people who are very stressed.
Yeah, I mean, thank you for this meeting. We're really thankful for this. And yeah, I don't think anyone has any other questions.
Okay, pleasure meeting you guys. Take care. Thanks for inviting me.
Okay, thank you. We'll contact you if